setting up a hypothesis test. Example 2. In a sample of n equal 80 National Basketball Association or NBA games, the proportion won by the home team, p hat, 50 out of 80 or 0.625 at the alpha equal 0.05 level of significance. Does this sample provide sufficient evidence of a home advantage? Well, let's think about why there might be a home advantage, or why the home team might be more likely to win. So the national basketball games or NBA games, you might have a team, for example, from Philadelphia traveling to Los Angeles, and it's maybe a plane ride of several hours in the air, maybe a 6-hour plane ride. There's a 3-hour time difference, and they're staying in hotels, and the team is staying in hotels. They're playing in an unfamiliar court, so those what might be some reasons where the home team might be at an advantage because they don't have to travel. And also, the home team has the home crowd cheering for them. So I think if you have people cheering for you, you have more likely to have give you a little bit extra energy to make that little extra effort to win the game. So those are some reasons why there might be a home advantage. So anyway, we want to test whether this sample provides enough evidence to say there's a home advantage. So in this sample, the home team won more than half the games, but that could have happened by chance. So we want to test whether this sample gives enough evidence of a home advantage. And I'll make a little diagram to sort of illustrate the relationship between the sample and the population. So in a sample of n equal 80 games, the proportion won by the home team, or p hat, 50 out of 80 or 0.625 as a decimal if you divide. Now this sample is taken from a larger population. In the population of all past and future NBA games, the proportion won by home team in the long run P, and that's, we don't know what that is. So our best guess based on this sample is that the proportion won by the home team in the long run would be 0.625, but we don't know that. That might have, if we took a different sample of 80 games, maybe only 40 would be won by the home team, or maybe 60, maybe more would be won. But this is just one sample. So we want to compare it to the proportion won by the home team if there's no home advantage. So if no home advantage, proportion won by the home team in the long run and if there's no home advantage, then we would expect the home team to win half the games, or as a decimal, 0.5. Okay. Some books call this P0, or in some textbooks you might see P0 equal to 0.5 to distinguish. So we have P represents our unknown population mean, and sometimes they use P0 to just to distinguish it from the unknown population mean. But the Triola textbook uses p for both of these without the p0 in there. Okay, so that's this diagram shows the relationship between the sample and the population. Okay, so more formally, set up the hypotheses. We want to test with, let's say, 95% confidence or 5% doubt. We want to test H0 or H0, p equal 0.5. There's no home advantage versus H1, p is greater than 0.5. There is a home advantage. Okay, so let's just go over some of the terminology. The null hypothesis, most textbooks always have an equal sign in the null hypothesis, H0. So an H0 is p is equal to 0.5. In some books, you might see a greater than or equal to or less than or equal to symbol in H0, but it always includes equal, and it's always sort of the reverse of whatever H1 is. The population proportion, that's unknown. That's represented by p. That's unknown. The null value, that's going to be the value of p if H0 is true. That's 0.5. Or in some books you might see p0 is equal to 0.5. The other null value, that's the value of that's the proportion of games that are lost by the home team. So that's going to represented by q or q0, and it's going to be 1 minus p, 1 minus 0.5, which in this case is 0.5. So this is the q would be the proportion of games lost by the home team. The alternative hypothesis, the Triola textbook uses H1. Some books use HA to represent the alternative hypothesis, and usually that's what we're trying to prove. We're trying to prove there is the home advantage. So if we have a left-tailed test, would have a less than symbol. Right-tailed test has a greater than symbol. A two-tailed test has a not equal to symbol. And for our example, we have a greater than symbol. So we're doing a right-tailed test. If the home team wins less than half the games, we're not going to say there's a home advantage. Is that we only say there's a home advantage if the home team wins more than half the games. So that's a right-tailed test. Okay, the significance level, I like to call it the level of doubt, and that's actually the probability of a type 1 error, and we'll usually use 0.05. Sometimes we might use 0.01. It's up to the researcher to decide how much doubt they want to have, and the most common levels are 0.05 or 0.01. If you want to be very sure of not making a type 1 error, you might see 0.001 for your level of doubt. Level of confidence is 1 minus the level of doubt. So 1 minus, in our case, 1 minus 0.05, which is 0.95. So we want to be 95% confident in our conclusion. The sample size, in this case, was 80, and the sample proportion p hat, x over n, so it's 50 over 80, which is 0.625. So 50 divided by 80 is 0.625. The letter x, which is 50, in the numerator is called a binomial random variable. It's binomial because each game has two possible outcomes, either won or lost. We'll ignore the possibility of a tie here. We'll say each game is either won or lost. It's a random variable because the number of games won can vary randomly from one sample to another. Okay, so the first step in testing the hypotheses is to check whether n times p is at least 5 and n times q is at least 5. So this and here we're going to use the null value of p. We don't know the population proportion p, but we know the null value. So 80 times 0.5 is 40, and is that greater than or equal to 5? That's a yes. And 80 times 0.5, q is also 0.5, 40 greater than or equal to 5, and that's a yes. So we got two yeses here. We need two yeses in order to use the z table. Some books, some books use 10 here, or some books use strictly greater than 5. These numbers are kind of arbitrary, but we'll use, this is the standard that we'll use. If n times p and n times q are both at least 5, then we can use a shortcut with using the z table to compute the probabilities, and if not, then we'll have to use the exact probabilities using a tree diagram or binomial probabilities. But these are both at least 5, so we can proceed to the next step. If h naught is true, the sample proportion p hat has mean or expected value 0.5. That's the same as the null value. So in the long run, if we repeatedly take samples of size 80, in the long run, if h naught is true, then on the average they should agree with the population proportion, which is 0.5. And the standard deviation of p hat is represented by the Greek letters lowercase sigma, square root of p times q over n, square root of 0.5 times 0.5 divided by 80. And we can put these in the calculator the way it's written. The calculator knows something about the order of operations, so if we just type it in the way it's written, and don't push equals to the end, so second square root 0.5 times 0.5 divided by 80 equals, and I get approximately 0.0559 and 0.055901699. Okay, so I'm going to store this in memory on my calculator so I don't have to retype it later. Okay, so now we can compute the test statistic. Well, remember, you may recall from earlier in the course, the z-score is the score minus the mean divided by the standard deviation, so that's the same idea here. In this case, the score is our sample proportion. A sample proportion minus the mean, which is p, divided by the standard deviations, which is square root of pq over n. So we can put our sample proportion was 0.625, and the population proportion, if h naught is true, 0.5, and we already computed the standard deviation of p hat. That's the denominator here, 0.0559, 0.1699. Okay, so the calculator knows something about the order of operations, but it doesn't know about a long division bar. The short division symbol, the division indicated by the short division symbol comes before subtraction, but the long division bar that's underneath the subtraction sign comes after a subtraction in the order of operations. So we want to do the numerator first. We want to do the subtraction first. We have to sort of force the calculator to do the subtraction first by pushing equals to put in the 0.625 minus 0.5 and then push equals, and we'll get 0.125. We're trying to force the calculator to do the subtraction. It's going to want to do the division first. And then we can divide by, and I'll recall this thing from memory, and we get approximately 2.24. So that's our test statistic, that's our z-score, 2.24. And the next step is to look this number up in the table, in the z table. And let me go over this here. So we want the probability of getting a result this extreme if h naught is true. So we want the probability of z being greater than 2.24. And this is because we have a right-tailed test. So this is going to be over on the right side. The bell curve is symmetric, and if our score is exactly equal to mean, we'll get a z-score of 0. That will be in the middle. If our x score is above the mean, we'll get a positive z-score. It'll be on the right side of the bell. But we're using a right-tailed test with a left-tailed z-table. Our z-table is a left-tailed table. That's a common way for z-tables to be set up. Not all z-tables are set up that way, but we want to change the sign here, look up the opposite sign in the table, because our table is a left-tailed table, and we're using it with a right-tailed test. So we want the probability z is less than a negative 2.24. So that would be at the other extreme. It's going to be on the other tail. Corresponds to this area here. And then so we want to go to the z-table and look in row negative 2.2 and column 4. And let's see what we get. So negative 2.2 and column 4, it looks like 0.0125. 0.0125. Okay, so that's our p-value. This is our p-value here. And because our p-value is less than alpha, we reject h naught with 95% confidence and conclude there is a home advantage. So the p-value of 0.05 is less than alpha, which is 0.05. And it might help to compare these if we add extra zeros, so we have the same number of digits after the decimal point. So if we add 2 zeros here, it makes it a little bit easier to compare. We have alpha equal 0.05, but if we add extra zeros on the end, so they have an equal number of zeros, then we can just look at what the numbers, compare the numbers that comes after the leading zero. So 125 is less than 500, so that means that 0.0125 is less than 0.05. It's less than alpha. So we can conclude there is a home advantage with 95% confidence. Okay, so there's a shortcut. If we use Triola's range rule of thumb part 2 for a right-tailed test at the 0.05 level of significance, any test statistic more than 2 will provide sufficient evidence to reject h naught. So our test statistic of 2.24 is more than 2, so even without looking up the p-value, we can reject h naught with 95% confidence and conclude that the new drug has a higher cure rate than the old. This shortcut is not as accurate as the p-value method. It's just sort of a rough estimate for whether we reject h naught or not. And you can kind of use that as a check. So if you get one result using the table and a different result using the shortcut, that might be a clue to check your work. But if you check your work and it's still different, just keep in mind the shortcut is not as accurate as the using the z-table. Okay, so a comment, we compared our p-value to alpha equal 0.05, but if we want to lower our chance of a type 1 error, which would be rejecting h0 when h0 is true, we can compare the p-value to 0.01 or 0.001. So if we had used alpha equal 0.01, our p-value is actually more than, in this case, the p-value is more than alpha of 0.0125 is greater than alpha equal 0.01. And again, it makes it easier to compare if we add trailing zeros, so they have equal number of digits after the decimal point. So 125 is more than 100, so that means that 0.0125 is more than 0.01. So that means in this case we would fail to reject h0. Fail to reject h0. Sample does not provide enough evidence to say there's a home advantage. Okay, technically we never accept h0. You might, the language of failing to reject with a double negative is at times a little awkward, and so you might actually see even in textbooks or in my lab, you might see language suggesting that we accept h0, but technically we don't accept h0 because it might be a larger sample would provide stronger evidence. So technically either we reject h0 or we don't know. In this case we don't. At this level of significance, we don't have enough evidence to reject h0, so we don't know whether there's a home advantage or not. And some researchers will simply report a p-value without specifying alpha. Generally, the lower the p-value, the stronger the conclusion. So this is a chart gives sort of a guideline for interpreting p-values. P-value between 0.1 and 1, little evidence against h0. Between 0.05 and 0.1, some evidence. Between 0.01 and 0.05, moderate evidence. Between 0.001 and 0.01, strong evidence, and so forth. Again, we can, if we add trailing zeros, it makes it easier to compare these numbers. So I'm going to add trailing zeros here. We have 0, 0, 0. This one only has 2 digits, so I'll add 2 zeros here. That one only has 1 digit, so I'll add 3 zeros. 2 zeros, 2 zeros. This one has 3 digits already. I'll just add 1 0. Okay, so our p-value .0125 is going to be between 0.01 and 0.05. This is in this case, our sample provides moderate evidence of a home advantage. So the p-value of 0.0125 is between 0.0100 and 0.0500. So in the chart they just had 2 digits to the left of the decimal, but I added these extra zeros to make it easier to compare. And if you just look at what comes after the leading zeros, 125 is between 100 and 500. So that means the sample provides moderate evidence. It's between 0.01 and 0.05 provides moderate evidence of a home advantage. Okay. Okay, so I'll make a little diagram here showing possible outcomes of hypothesis testing. So either H naught is true or H1 is true, and either we reject H naught. I'll start with fail to reject H naught. Fail to reject H naught, or reject H naught. Okay, so either H naught is true or H1 is true. Either we fail to reject H naught or we reject H naught. So if we reject H naught and H naught is true, that's called a type 1 error. And that's probability of that happening is alpha. That's a type 1 error. And alpha is our desired level of type 1 error. So that's established by the researcher. And then if we fail to reject H naught when H naught is true, that's 1 minus alpha. That's our confidence level. And then the Greek letter beta is it looks like a B, and that's a probability of a type 2 error. So if we fail to reject H naught and H1 is true, that's called a type 2 error. That probability is beta. Usually we don't know what beta is. Alpha is established by the researcher, and in order to compute beta, we need a specific value for the population proportion if HA is true. So our H1 is true. So we don't have a specific value to put in. So for the null hypothesis, we have a specific value for P. It's 0.5. For the alternative, the alternative just says that P is greater than 0.5. So that maybe it's 0.6, maybe it's 0.7, but we don't have a specific number. We need a specific number in the alternative hypothesis in order to compute beta. So beta is not usually given or computed. That's the probability of type 2 error. And then 1 minus beta is called the power of the test. Okay, so that's just some of the terminology. So we have 4 possibilities. We could reject H naught. We could fail to reject H naught if H naught is true. Reject H naught if H naught is true. Fail to reject H naught if H1 is true. Reject H naught if H1 is true. So 2 of these would be errors, and 2 of these conclusions would be correct conclusions. And I express the terminology down at the bottom of the page here. 1 minus alpha is our desired level of confidence. Greek letter alpha, desired level of significance. I like to call it the level of doubt. It's the probability of a type 1 error. P-value is actual level of doubt. And more precisely, it's the probability of getting a result this extreme if H naught is true. Beta is probability of a type 2 error. 1 minus beta is the power of the test. Okay, so some exercises on this. Is it possible we made a type 1 error in example 2. So in example 2, we rejected H0. So if you reject H0, you always take a chance of a type 1 error. Okay, so yes, because we rejected H0. Is it possible we made a type 2 error in example 2? Type 2 error can only occur if you fail to reject H0, but we rejected H0, so we would not have made a type 2 error. So this is no, because we failed to reject H0. No, because we rejected H0. Type 2 error occurs only if you fail to reject H0. If in example 2, if alpha had been 0.01 instead of 0.05, what type of error had been made? Well, the p-value of 0.0125 is greater than alpha. In this case, alpha is 0.01. If you want, you can add some trailing zeros. 125 is more than 100. So fail to reject H0. So if we fail to reject H0, then possibly we're making a type 2 error. Possibly making a type 2 error. So whether you reject H0 or fail to reject H0, you always take a chance of an error. So if you reject H0, you take a chance of making a type 1 error. If you fail to reject H0, you take a chance of making a type 2 error. And the best way to lower the chance of either type of error is to increase the sample size, but the drawback there is that the larger samples are more expensive. So there's a little bit of a trade-off between being confident in your results and the cost of a larger sample. And that concludes this presentation.